It's all yours.
Okay, great. So we're just going to continue for the next 15 minutes, picking back up where you left off. And just let me know if you have any questions, but you can keep answering the questions from the worksheet looking at the data in DS9. So let me know if you have any questions. But for now, I'm going to turn off my camera and turn off my microphone, but I'll be here. And let you guys work for another 15 minutes. And then in 15 minutes, when there's about 15 minutes left in the class, we'll come back on and I'll explain kind of what I was looking for some of the answers. All right. I see a question in the chat, and somebody asked, what do I mean by hot pixels? Sorry, the hot pixels are just kind of the pixels that are much brighter because of the dark current, and they're often called hot pixels. They're also called like bad pixels or bright pixels. It was just hot pixels was what I had used in the slides. But yeah, the brighter pixels on the dark frame because of the dark current.
Hi, Aurora. You have a second question in the chat. Okay.
Yep. Okay, I see it. Yes. So the question asked, where can you see the pixels in the spectrum? So question 5. Oh, okay. Cool. Let me just share my screen to show you what I meant by that question. Okay. Great. So I'm sharing my DS9 window, and this is the flat. You can see I'm zoomed into a small region. So I was just wondering, the question asked on question 5, how many pixels wide are the illuminated orders in the flat frame? So yeah, I was just hoping that to get like a rough estimate of how many pixels it is from top to bottom of some of the illuminated orders on the flat. So you can, if you have your cursor here, you can see my cursor, and then you can also see it says image X 1041 and Y is 1154. So that's pixel number 1154 in the Y direction. So then I can, if I move my cursor down, the X stays the same, but the Y is moving. So I was just hoping to see this order that I'm looking at is about 1126 minus, oh, no, sorry, wrong way. 115, yeah, about 1156 minus 1126. So it's about 20 pixels wide. That's kind of what I was hoping to see. So then you can do this on both the flat frames and the spectral frames and see if there's a difference in how wide these orders are. Okay, let me stop sharing. Hopefully that answered that question. Oh, you asked for in the spectrum frame. So you can do basically the exact same thing. And instead of looking at, so for the flat frame, the orders are a bit wider, you'll see. In the spectrum frame, you can actually do the exact same thing. And just the number that you'll get will be a bit different. It should be a bit less.
Hi, Aurora. You have a next question.
I see. Actually, I have two questions. So
You do?
let me first go back to the same one about the spectrum frame instead of the flat frame. So okay, maybe I think, let's see if, I think I know the problem. Okay, so here's my spectrum frame and I'm zoomed in, but right now it doesn't look like anything. So let me zoom out. And in order to see the trace of the orders, you really have to play with the scale. Put it on Z scale. Okay, so if I put it on Z scale, I can start to see the trace of the orders. So now I can play with how bright it is and try to really see the orders as best as I can. And then now that I can, well, let's see. Now that I can see the orders better, I'm going to zoom in. And I can do the same thing for seeing how many pixels this spectrum is compared to the flat spectrum. So yeah, in order to actually see the trace here of the spectrum, you have to really play with the scale. Hopefully that helped. Okay, and then the other question was, I heard that some telescopes had CCDs that are cooled enough so it isn't necessary to take dark frames. Is this for reducing observing time? Yeah, so definitely the cooler the CCD is kept, the less that you actually really need to use the dark frames, because there's not going to be very many thermal photons that are exciting the electrons. And dark frames don't really change much on the overhead because you can take them actually during the day, because you don't need to be opening the telescope or looking at any objects. But if you are reducing the number of dark pixels, the dark current, these are corrections. So corrections are always going to have uncertainty and error. It's always better to try to reduce the source of noise before it starts than to let the source of noise be large and then try to correct for it. So even though dark frames don't really cost much overhead to your observing because you can take them during the day, it's always better to try to get rid of all of these sources of noise before you start. Okay, so actually now it's there's only 15 minutes left. So I think I'll start going over some answers. And if you have more questions, just write them in the chat. Great. So let me share my screen and bring up the dark frame first. Okay, here's my DS9 frame. And I'm going to keep it zoomed in so that I actually might even zoom in farther so I can look at some of these hot pixels. Okay, so now I can see that there's a range of different hot pixels. Some of them look dimmer and some of them look brighter. But if I put my mouse over this one, wow, this has a huge value. So I can see, okay, if I put my mouse over here, the value is usually around 189. But if I put my mouse right on the hot pixel, the value is over 200,000. let's look at this one's even brighter. So this one's over 500,000 for this hot pixel. So some of these hot pixels can be really bright, and I want you to remember this going forward. So let's see, did I have any other questions about, okay, so we can do question number 2 also with the dark frames, but now I have to zoom back out. Okay, so I was wondering how many pixels wide is this CCD? So if I put my mouse all the way over at this edge, you can see that my X pixel is about 0, great. And now if I go all the way to this edge, my X pixel is about 2040. So this CCD is about 2040 pixels in the X direction. So let's check the Y direction now. The 0 is actually down here. So now you can see my Y value is about 4 pixels, so I'm not all the way at the very bottom. But if I go up to the top, my Y value is also 2045. So this is a 2045 by 2045 pixel CCD. And about a 2000 by 2000 pixel CCD is very common. Most near infrared and optical CCDs that are used for spectroscopy are about this size. Okay. So then the next few are about the flat frames. So I'm going to close this and stop sharing and then reshare when I open the flat frame. Okay. Okay, so now here I'm sharing my flat frame, and let's zoom out. All right, here you can easily see all of the orders, and by looking at the flat frame, we can kind of, the reason that we use flat frames is to tell the pixels, the CCD's response function at different places. So we want to know if this CCD was perfect, we should have the same number of counts on the edges of the CCD as in the center of the CCD, because we're taking a spectrum of a sheet, a screen that has been uniformly illuminated. So everywhere we should have a very similar number of counts, but we're going to see that the CCD is not perfect. So in the center of the CCD, at the center of one of my orders, the value I have in the counts is about 21,000. But over here at this edge, the value of my counts is about 1,000. And over here, in the center of the order, the value of the counts is about 2,000. And so there's a huge difference in the response in the center of the CCD as the edges of the CCD. And we need to correct for this. And so this is what we're correcting for with the flat frame. And so to correct for this, we basically average all of the pixels to 1, and then we divide by that in all of the other frames. So to do the flat, we average to 1, and then we divide by the flat. And this should help to correct for all of the changes from the edges of the CCD to the center of the CCD. And you also get, at the top and bottom, you also get fall off. So let's see. In the center of the bottom order, I get 17,000 counts, whereas in the center of a middle order, I get closer to 21,000 counts. And at the center of the order at the top, I get about 20,000 counts. So the bottom of the CCD seems to be worse than the top of the CCD, but the center of the CCD is the best. And all of this is taken into account with the flats.
Hi, Aurora, you have another question in the chat?
Mm-hmm. Oh,
Will
yes.
you also look at the header?
Yes, I was supposed to tell you that when I started, but you can look at the header here by going to File and then Header. And this will list the giant long header for the frame. So yeah, you can see that this was the iShell spectrograph that I told you was the instrument that I was using. And you can see that these are my observations, and I did them in 2018. A bunch of other information.
Yes, they can reproduce what you just did on their own computers, because the fact that you are sharing the screen of DS9, the header, when you press it, it opens a new window. So we are not seeing the new window.
Sorry, let me just share my full screen so you can see. Okay, here's my entire screen. So now if I click on the file button and then the header button, it pops up the full header. So this is what I was showing you before, that it's the iShell spectrograph. It has the PI, it has the date, and all of that. Okay. And I'll go back to just sharing my screen here. Okay, and I kind of already answered the next one, but I'll just quickly talk about that. Oops. Okay, so for the next question, I was asking how wide are the flat frame orders? And so I kind of already talked about this, and I think we came to the conclusion that they're about 20 pixels wide, if I remember correctly. Let's see, okay. So 1336, 1366. So they're 30 pixels wide about. So I'm going to stop sharing this one and go to the spectrum frame again.
You have another question on the chat.
Okay.
Is this difference in counts between the edges and the center due to the way the shell works?
Right. Okay. Yeah. So it's a combination of the way the shell works and the way that the CCD works. So the way that the CCD works, we are hoping to correct for with the flats mostly. And still, when we remove the way that the CCD has a response function, then you still get that blaze function, and that's mostly from the way that the shell works. So you have two effects. You have the way that the shell works and the way that the CCD works. And what we're mostly correcting for with the flats is the way that the CCD has a response function. And then when you're still left with this blaze function, this is mostly trying to, getting rid of that is mostly trying to account for how the shell works. Okay. And then sharing my screen for the frame again. Let's see. So then I was wondering how many pixels wide is the CCD, is the trace from the target instead of from the full flat frame. So again, you do have to do a bit of changing on the scale here. Oops. And I'll just change the scale. And okay, so you can see here that instead of, before we had the height of this order was 30 pixels. Now it's only about 4 pixels or something much smaller. Let's zoom in to see. So now you can see the start is at about 1140. and the end is at about 1135. So it's about 5 pixels instead of 30 pixels. And the reason for that is because when we are doing the flat frame, we have the entire slit being illuminated. But when we're doing the star frame, the star is a point source. And so it's sitting at a very specific point on the slit, and the rest of the slit is getting sky, is looking at the sky. And so you can kind of see that it's a bit brighter right around the star. And so that's probably a bit of sky background emission or thermal emission from the sky. And then in between, it's darkest.
You have another question on the chat.
Okay.
With a CMOS camera, can you get information like what you do in a CCD camera?
I'm not sure any specifics about a CMOS camera. The person who asked the question, do you have more information? Yeah, if you have more information, let me know. I'm not sure that much about CMOS cameras. So sorry, I don't know how to answer that one very well. Okay. So you had to, when you were looking at the spectrum file, you had to really change the scale in order to get these, in order to get the actual like trace from the spectrum to come out. Because the really dominant source, if I go back, if I go back to how the image originally popped up, the dominant source of a lot of these bright pixels are actually the dark current. And so you can see here that the dark current subtraction is an important step for this CCD. So it might not be important for other CCDs, but you can see that these hot pixels are really dominating the CCD image here. So the dark current subtraction is important here.
I already have some discussion in the chat about the CMOS camera. CMOS camera is a regular DSLR camera, so it has a regular CCD. I will guess that the answer is that it will work in the same way, DSLR, but the CCD camera that you have on a telescope is way, way more effective than a regular CCD in a DSLR camera. And then you have a question. The pixel coverage between a spectrum and flat change for an extended object?
Right. Yes. So if your object is extended and taking up more of the slit, then you're going to get a wider. Let's go back here and we'll scale this. So you can see here, this is only 4 pixels. So if I'm looking at an object that's extended, you're going to start seeing more and more pixels from the actual spectrum that are being illuminated. If the object takes up the entire slit, you're going to get the same 30 pixels width of the order if your object takes up the entire slit. For the point source here, we're only 4 pixels. But for larger and larger, more extended sources, you're going to get larger traces. And up until it takes up the entire slit, it's going to be the same as the flat. Hopefully that answers that question. And then the last question, I was just hoping that you could do a quick order of magnitude for signal to noise. And you can quickly calculate that based on the number of counts inside of the spectrum. So the number of counts inside the spectrum at the center versus the number of counts inside the spectrum at the edge. And then you can divide that by the average number of counts in between the orders. And when I quickly did this on one of the spectra yesterday, I was getting maybe signal to noise ratios of 10 or something on the edges, and maybe signal to noise ratios of 50 or something in the center. But it's kind of the end, so I think that we'll quit there for today, unless people have more questions.
No, so far.
I don't see any.
Okay, so remember that questions that you might have through the day or that you can come up with, you can just write to Aurora. Here on the screen, you're seeing her email address, so you can send them the questions you might have, and then she will be happy to answer all of your questions. And the happy part is added by me, by the way. And so thank you very much, Aurora. It was a great lecture today. The exercises were amazing. So thank you very much. See you all tomorrow at same time through the same YouTube channel. Thank you very much.
Yep, thank you.